This expresses the minimum thickness appearing in the image. Use the collimation, beam collimation, find every option. E.g., if you have an option of 64, it won't work with 6401, 6401.4, or 3201.5. It can use half of them, once 2.5, or 401.4, and so on. And a quarter of 3212 is used in their text, just like we do here. For example, we say 1212 or 4114 or something like that, and so on. Well, this varies from one function to another, from one company to another, and from one model to another, depending on the type of ray or the type of detectors you have. But you need to understand what these numbers mean. 16 means 16 detector heads. In summary, the number next to it represents the thickness of the section being used, which is the product of the two standing together. And this relates to the coverage area. This whole concept is called beam collimation. Beam collimation is the first type of detector, which is the linear array, where all the elements present have equal beam widths. Then there is the second type, which is the performance. Okay, doctor. Look, doctor, so that this part doesn't confuse you, the beam collimation is what you take that determines the thickness or the area you want. Right? Well, I don't have the ADEX rate with me right now. Here we have collimation, and here, as you can clearly see, I have a patient and a detector. Now, to put it simply. And clearly, I have essentially 16 rows of detectors. If I want to use less than 16, what should I do? Should I change the beam width from the collimator above, or should I change the post collimator? The beam width here will not change for you, but I change the post collimator. Why? Because I want to take a specific thickness, which is exactly what I need in this particular context. In this case, the collimation here is determined based on how many you are using. If you are using all 16, then the beam here is 16 in 1, which means 16 millimeters. This is what you will cover. Now, 16 times 2.5 in this specific scenario. So 16.5 remains 8 millimeters, which means in one rotation you are scanning 8 millimeters. But in reality, you are exposing the entire body with me, doctor. I mean, in reality, you are exposing the entire body, but you are collecting data to reach the resolution you need. But it's at 8 millimeters of pitch. Is that understood? It decreases? It decreases? No, it doesn't disappear. It decreases. That's true. It takes part outside the active elements, making the beam a bit larger to ensure that the number is outside the area where detection is taking place. So it decreases. Now, regarding the topic in the context of the detectors, it was mentioned that I will not keep all my raw detectors or all the elements having the same width, for example, 1 millimeter. Instead, it was said that I will have a few detectors, like the one outside, which is 5 millimeters, the one next to it, which is 2.5 millimeters, the one next to that, which is 1.5 millimeters, and the one in the center, which is 1 millimeter. So, I have, for example, 8 elements with different sizes. This means that this technique, or as we say, the manufacturer has designed this setup to provide several options for collimation. 2 in 1 millimeter is used, 2 in 1 millimeter is used, 2 in 1 millimeter is used, 2 in 1 millimeter is used. For example, To specifically cover a specific area of approximately 2 millimeters for me, and to get an image of 1 millimeter, I would use the detector that is 1 millimeter, and I would use two of them in total. Now, if I want to use two detectors of 2.5 millimeters by 2.5 millimeters, I would take one of those and one of the 1.5 millimeter detectors next to it. In summary, for me, every two detectors are essentially like one row. Why? Because I will take the data from these two together. They represent 2.5 millimeters. The two adjacent to them also represent 2.5 millimeters. So, 4 at 5 millimeters, I will take the largest one, which is 5 millimeters. The one adjacent to it is 1, 1.5, and 2.5, which also makes 5 millimeters. So, you have used the 4 as if I actually have several rows. However, since it is set up as a band or a connection between several rows, it needs to adjust the beam collimation or provide more in terms of what it starts to change in what it uses. The problem with this is that the process of linking all of this is connected to something called a specific system that takes data from my detectors and sends it to the computer for processing. In essence, well, when you have different sizes of detectors, it complicates things a bit and you need more data channels to handle this situation. Plus, if there is any problem with the detectors, the process of replacement or repair becomes difficult because not all detectors are similar. For example, sometimes an engineer comes in and there is a specific issue. So sometimes he replaces his device or the problematic item, for example, or he replaces it with something else, puts it in place, and starts working. In this case, you are in a situation where you are certainly bound and restricted, and you won't be able to do this. And that without much difficulty. So for them, these matters have become expensive, as they might need to replace the entire module or the entire detector if there is an error or some issue. They cannot simply do a replacement or switch from the inner detector to the outer detector, depending on where the problem is. The same idea applies to the concept of binning or combination, which makes it easier for me. When I take data from two detectors or two rows of detectors together, it's as if I'm working with both as one detector. This simplifies things for me. If I want to scan a large area, I have no issues. If I want more resolution, I also have no problem. I will keep my collimation tight and work with just one or two detectors with a small thickness. It depends, doctor. Based on the dimensions I mentioned, it would be 1 millimeter. For example, here, what are you working with? Is it 2 by 2.5 or 4 by 5 or 2 by 1? It all depends on the beam. I'm working with 2 by 2.5, is that correct? So, I will take what? I took two rows. I took one row of 1 millimeter and added another row and a half. So that makes 2.5. This 2.5 means 2. 2 what? 2 rows of the detector. Now I don't have the capability to take, for example, 2 rows, each of which is 2.5. So what do? I take 2 rows and consider them as if they are 1. These 2 rows are 1, 1.5, 1, 1, 1. So that makes 2.5. I take 2 more rows like them. 1, 1.5, 1, 1. So that makes 2 times 2.5. So, what's the thickness for me? 2.5 millimeters. Can I go below this thickness? I mean, if I go down to a volume of 2.5 millimeters, can I do it with 1 millimeter or 0.5 millimeter? You can't, because the raw data you have is 2.5 millimeters. You can't go below your raw data. If you took 1 millimeter, then the minimum thickness is 1 millimeter. As for the detector size you are working with, if you are doing collimation, say for example 16.5, that means your coverage area is 8 millimeters. Does that mean your measurement is 8 millimeters? With a thickness of 0.5 millimeters, you can perform reconstruction, which I call post-processing. For me, I can produce images at thicknesses of 1, 2, 5, 10, and even 50. But I cannot do it at 0.25. I can't, because the raw data I received is 0.25. This volume corresponds to the many images you have on the device. Please scroll through them and check the ones that are 1 millimeters or 0.5 meters. For example, you can create a new reconstructed volume with 1 or 1.5 as you wish. But what is your beam collimation? This is the point. If your beam collimation is 16.5, then you should output half of 16.1, which means output 1 of 16.1.4. So output 1 1/4, which means output 1. If it is 1 1/4, then output 1 1/4. Sorry, doctor, I didn't gather how much is in 0.5. For example, approximately 16.5. Okay. But what is this text based on? No, it's based on the detector width. That's what I'm telling you about in the multi-detector or multi-slice that determines the thickness of the detector. Oh, if I work at 16 in the middle, then this would be another detector. But the minimum is 1, so it won't even open for you. It won't open for you absolutely in any way at all. The whole thing won't open for you. The machine itself tells you, no, I can't do more than this. For example, this image I have here, 24 detector rows. Okay, there is a group of detectors in the middle with a thickness of 0.6 millimeter. The large detectors we are seeing are 1.2 millimeters. Now, if I say I want to work with 16 at 0.6 millimeters, I will be working on the part in the middle. This is the part that has the active elements, or the active detectors that I will be working on. Okay, if I say I want to work with 16 at 1.2 millimeters, what will the 1.2 do? I will work with all the rows I have that are available, but every 2 detectors that were 0.6 with 0.6. I will consider them as 1 row of detectors. Right, doctors? It's like you're doing a pairing or combinations between the detectors in the center. For me, every 2 will be paired together. So if I operate at 16 in 1.2 millimeter, can I reconstruct a 0.6 millimeter image or not? No, you can't. Good. So, if I operate at 16 in 0.6, can I also do half a millimeter? Again, you can't. You can only output 0.6. All right, where is this? Okay, great. So, the question here is, what will he take this with? This goes back to the configuration of the detector itself, Dr. Hani. The configuration means the shape of it, which is crucial for its functionality and accuracy in detecting specific elements. So, can I work today with 2.5 millimeters? Or can I work with 1.5 millimeters? The choice of millimeter size can significantly impact the precision and effectiveness of the detection process. But the question here is, where is the position of the 2.5 millimeters for me? I mean, when I say 1.5 millimeters, Is it at the center of my beam? If the beam is here, is it better for me to work on it or to work on the lateral row of the detectors? The position of the beam in relation to the detector is vital as it determines the accuracy and reliability of the readings obtained. Understanding these configurations and their implications is essential for optimal performance. The idea here for me is that today, the closer you are to the center of your X-ray beam, the higher your detection efficiency and geometric efficiency will be. So, what makes him choose 2.5, which is far from the center of the detector, and work on it, even if he is going to do collimation and go up to 2.5? It's logical for him to work with the configuration that is easier or that gives higher detection efficiency. The hybrid is like the example we were talking about, which is the idea that I don't have a different set or different sizes. I had this linear, everything like some adaptive. You have a set, meaning every 2 rows, for example, or every 2 rows, I have a certain configuration here. Then it tells you, no, here it works like the linear, but my center is just giving you the option to be, for example, 0.5 millimeters, and the outer part for me, or in this example, has 8 rows of detectors at 0.5 millimeters in the center, and on the periphery, there are 6 rows of detectors at 1 millimeter. So it gives you the combination you can work with: 4 at 0.5, 4 at 1, 4 at 2 millimeter slices. Accordingly, you have a half, so it will take here 4 rows, each one of them half a millimeter. Okay, but no, I want to work with 4 at 1, 4 at 1. So half with half, half with half, each one representing 1. This is 1 together, and this is 1, and this is 1, and this is 1. You have 4 columns, and you can create combinations between them, capturing 4 by 2. The same idea applies here. For example, this is 1 and 1. So these are 2, and this is half and half, which makes 4 by half equals 2. This is 4 by half equals 2, and this is 1 and 1, so that makes 2. These are the collimations available in this array or in this detector configuration. When you look at any machine, it will provide you with configurations, and there are things it allows you to do and things it does not. For example, it will tell you that you can work with this collimation, or you might not be able to. You might say, I want to work with 64, especially in the 64 machine at 0.5, and it might tell you, no, work with 64 at 1.25. If you want to go down to 0.5, work with 32. Why? Because it has the 32 in the middle that works with 0.5. This goes back to what you mentioned about the detector configuration and the specifications of the machines coming to you. How are they set up, and what type of detector is used? Of course, companies tend to play around with these details and don't reveal their secrets. They don't disclose what techniques or methods they rely on for operation. Most of what I've seen today is either a linear array or the hybrid type. The multi-topic approach is no longer used. It's either the hybrid or the linear, which is all the same. We talked about the pitch last time, and we thought it over, right? Or should we revisit it? There is something very important. The man who developed this CT in the 1970s is Jeffrey Hounsfield, a biomedical engineer, and he was accompanied by a physicist from South Africa named Cormac. The two of them received the Nobel Prize. The Hounsfield unit comes from the biomedical engineer who was around in 1972, meaning the equation that expresses the CT number that we use and that you all use in measurements every day. The Hounsfield unit is about what? It is about the difference in attenuation. So I am now simplifying it. If I have an X-ray tube and I have a detector, for example, I call the incident photon inode, and the one that passes through, I call it transmitted. The one that reaches my detector is calculated using an equation that says it equals inode times e to the power of minus mu times x, where x is my thickness, and mu is the attenuation coefficient. The attenuation coefficient of the organ or object that I am imaging certainly indicates what the attenuation coefficient is, which is the ability of this organ or object to attenuate radiation by a certain amount. From this equation, you can in fact determine the transmitted I for yourself. The main factor that the topic indeed depends heavily on is the attenuation coefficient. This attenuation coefficient varies specifically from one material to another. You have water, fat, bone, and air. Each has its own attenuation coefficient. When we look for the most abundant substance in the body, water will be our benchmark to work with. We see the value of the attenuation coefficient for water, and this will be our reference. That's why quality control is, as a matter of fact, conducted using this. They say they will use it and do water calibration or water phantom calibration, which uses water to see the CT number for water, which is around 0 plus or minus 4. Plus our arms are for 0, plus our arms are for 0, plus our arms are for 0. How is the CT number calculated? Simply put, it involves taking the Hounsfield unit, which is the attenuation of the tissue minus the attenuation of water, divided by the attenuation of water, multiplied by 1000. In this case, the tissue is water, so the entire term becomes 0. 0 minus 0 over 0 times 1000 equals 0. They said they would add plus or minus 4 to account for the possible variation in your value. If you notice, in the equation, water is used, and when you replace it with the bone attenuation and the soft tissue attenuation, they found that the bone has a high value. For example, 500, the soft tissue was around 40, while fat was about 100, and air was 1000. You will always find that the attenuation that is less than water comes out negative because in this equation, the attenuation of the tissue, water, is greater than that of the other tissues, which is why water has a negative sign. The bone or fat has an attenuation value of 550, air has 1000, and water has 0, and so on. You all know these numbers better than I do. This expresses the amount of attenuation that occurred. The attenuation is considered the significant factor in this whole story. It is the significant factor in all these values which express the CT number of the tissues present. So the point is, we will explain it in image reconstruction. Here in image contrast, I currently have this organ, which is this large circle, and inside it are two high-density objects relative to me, located by the X-ray tube. As it rotates, it emits an X-ray beam, for example, at every angle. Let's assume every 1 degree. So here we have 0, 1, 2, and let's say 0, 1, 2, 3. At each angle, it starts capturing values that represent the attenuation of the object present. For instance, at angle 0, the X-ray beam had a certain shape, and the two objects appeared as if they were one. Why do they appear as one? Because it doesn't see them separately. It sees that the attenuation or transmitted beam that passed through the first object entered the second object and reached here. Thus, the beam profile or the data that appeared looks like it came from one object. So why did it create this curve? Well, it created this curve because of the way the X-ray beam interacts with the objects. Here is the object and the transmitted beam. and it comes here and here, meaning the X-ray is not passing through, but it is in my object. So this curve represents what? It represents the amount of attenuation that occurred. The highest attenuation occurred in the object itself, and thus the attenuation here was low, 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 while the value was high, 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 and then it decreases again at the edges in this area and this area. This is the curve represented from this angle. Now, when we move to angle number 1, 2 peaks started to appear. Why? Because it began to see this object, and each of these objects has its own attenuation profile. So the 2 peaks started to appear like this. When we reached angle number 2, it began to see them and see them apart because there was clear discrimination. It can distinguish and see the 2 objects here as separate. At angle number 3, it started to see them like this. So this data is what it received. Every angel I name it the angle I take, I call it. So this projection, my detector received it correctly. Now where should this data go, doctors? It should be placed correctly. In the end, where do I want it to go? What do I want to extract in the end? The image is fine. I want to take everything I have taken and return it again to the image, so it will be called.